This is AS2 Physics 2 paper in January 06, and this question is all based on refraction. The first question asks us to explain what is meant by refraction. Refraction is when a ray changes direction. At a boundary between two different substances then, or an interface between two different substances. Figure 2.2 below shows the interface between air and glass. So air is on the upper side and glass is on the lower side. Make additions to figure 2.1 to show what is meant by the terms angle of incidence and the angle of refraction. And the important thing is you have to label your diagram clearly. Now there are two marks for this, so there are two different aspects really that they're looking for. The first thing we're doing whenever we talk about refraction at any time, all measurements are taken to the normal. So the first thing we must add to our diagram is a normal. For that you need a protractor. Don't try to do this just with a ruler because it won't be accurate enough. So lay up your 90 degrees, mark your 180 and 0, and then with your ruler simply join. Line it up and draw a normal, and make the normal a significant size. And to make it obvious that you know, label this as the normal, and I would draw at a right angle to make sure that you're showing that you know that the normal is at right angles to the interface. The next thing, for an angle of incidence, for that we need an incident ray. So you can draw this ray at any angle of your choice. And it's not a ray unless you put an arrow on it. If you don't include the arrow, it's simply a line. And the angle of incidence is the angle between the ray and the normal. Then it asks us to show the angle of refraction. Again, we need to draw then a refracted ray, and remembering that whenever a ray enters from air into glass, it bends towards the normal. The angle of refraction then should be smaller. To avoid confusion in this, to make it smaller, lay your ruler along the line of incidence, and you can imagine where that line's going to be. Then bring it round so that the angle in here is getting smaller, and make it significantly so that it's obvious you know that the angle of refraction is smaller. And again, it must have an arrow to make it a ray, and put the R between the normal and the refracted ray. Avoid bringing your refracted ray round too far, because if it's too close to the normal, it has been over refracted. So again, it asks there for the angle of incidence, the angle of refraction, which we've clearly labelled, I and R, and label it with the letters that the question gives you. With regard to the marks and the mark scheme for that, there was one mark for drawing in your normal and making sure it was at 90 degrees, and for including arrows. So if you missed either of those, you would lose that mark. And the second mark is for I clearly and correctly labelled with the labels given in the question. Moving on then to part 3 of that question. The refractive index of glass is n. The speed of light in air is c, and that in glass is cg. Write down expressions relating n to the angles of incidence and refraction initially. So we're looking back at our diagram in part 2. We used I for the angle of incidence and R for the angle of refraction. And our equation is n equals sine of I over sine of R. The two speeds then, n equals the speed of light in air you were given to be c, so use c, use the correct notation given in the question, over the speed of light in glass, which is cg according to that question. Okay, moving on to the next part of the question then. You are given information about the refractive index n of a certain type of glass for different colours of light. So For the red light, the refractive index is 1.4794, and for the violet light, the refractive index is 1.4941. Now this does actually make sense to us because we know that in dispersion that violet light is refracted more than red light, and that's how we get to see the spectrum when white light is dispersed in a prism. So these two values are logical and do make sense to us. The question then asks us to calculate the difference between the speeds of red and violet light in the glass expressed as a percentage of the speed of red light. So we're interested in the speeds, but we haven't been given the speeds in the question. But we do know an equation that links the refractive index with the speed, and that is the refractive index N equals the speed of light in air C over the speed of light in the glass, which is going to be CR. And we want to find the speed of the red light in glass, so we'll rearrange the equation. CR equals C over N. The speed of any type of light in air is 3 by 10 to the power of 8, divided by the refractive index for red. And when you work that out, you get 2.0278 by 10 to the power of 8. Now I would go to at least 4 decimal places here in your figures, because there's very little variation here, and to be able to get a significant value you need to have the 4 decimal places. A good guide to the number of decimal places or the degree of accuracy to go to when you're doing these calculations is to refer to the degree of accuracy for the values quoted in the question and to follow that degree of accuracy. Now we repeat this process for violet light, so CV equals C over N, the exact same process, and that gives us 2.0079 by 10 to the power of 8. Now as we can see, there's not an awful lot of difference between these figures until we go down into the lower decimal places. So the change in speed as a percentage of the speed in red is 2.0278. Find the difference, 2.0079, all divided by the speed of light in red. We must remember that's by 10 to the power of 8. And then to turn it into a percentage, of course, we multiply by 100. So we get 0.98%. So to repeat that process again, we find the speed of red light in the glass, we find the speed of violet light in glass, and then to find the difference between them, we subtract the values divided by the speed of red light in glass and multiply that by 100, and we get actually a very low value of 0.98%. On to the next part of the question then. A parallel beam of light containing both red and violet colours enters a plain piece of glass from air at an angle of 60.00 degrees. Show that the angle of refraction of the red component is 35.83. Well, we've been given the angle of incidence. We want to find that the angle of refraction is 35.83. We're focusing on the red, and what we know is that n red is equal to sine I over sine R. So to rearrange that, because we're interested in finding the angle of refraction, sine of R is equal to sine I over n red. So R is equal to the inverse sine of sine of I over nr. So it's the inverse sine of sine of 60 divided by the refractive index for the red light, which is 1.4794. And when we work all that out, we can find that R is equal to 35.83 degrees QED. When doing questions of this nature, you must always remember to check that your calculator is in degrees. If you've been doing other work, you may find that you have your calculator in radians, so you must make sure that it's in degrees, or you'll find you'll be getting the wrong answers here and you won't be able to prove this. Part 2 of this section of the question: the beam disperses as it enters the glass. Calculate the angle between the red and violet components of the dispersed beam. Well, we have the angle of refraction already up here for the red, it's 35.83. We now need it for the violet. We need to find what it is for the violet to be able to make the comparison. So we follow the same process. NV equals sine I over sine R for the violet. R violet then is the inverse sine of sine of I over N violet. Remember, both the red and violet, looking at the question, entered the same angle of incidence. So we can put in here sine of 60 over N of violet, which in the previous part of our question was 1.4941. And that gives us an angle of 35.42 degrees for violet. So we want to find the angle between them. So the angle between the two colours, the red and the violet, is the difference between the two angles, which is 35.83 minus the 35.42, which is 0.41 degrees. And if you think back to the experiments that you've done in dispersion, that kind of angle sounds about right. So quite a long question then, covered several aspects. The definition of refraction, showing that you know your terms and that you know your equations to calculate refractive index, including the angle one and the speeds one. We then moved on to using the speeds of light and refractive index and then making a comparison of them. And finally we used the refractive index using the angles equation and again applied our knowledge in making comparisons of them.